In this example, we want to find any relative extrema of the function f of x equals 2x squared minus 3x plus 5, and then we'll throw it onto a graph. So first thing we want to do is we want to take the derivative of the function, because what we're going to end up doing is we're going to want to determine those critical values. In order to determine critical values, we need to know the derivative. So the derivative is going to be 2 times 2, which is 4x. 2 minus 1 is 1, so there's 4x there. Minus just 3. So that's going to be 1 minus 1 is 0, so the x drops out. 5 is a constant, so we have nothing there. So there's our derivative. Now we want to start determining critical values. And after we get critical values, then we're going to want to know the increasing or decreasing around these critical values. And that will tell us a lot about our graph. So we're going to set our derivative equal to 0, because that is going to tell us that where the derivative is equal to 0, that means that the graph flattens out. Not necessarily means it changes direction, but just knowing that it flattens out. So we're going to set our derivative equal to 0. It's a horizontal tangent. Solve for x. So 3, so 4x equals 3. Divide by 4. So x equals 3 over 4. What that means then is that at the x value of 3 over 4, we have a horizontal tangent. It's flattening out at that spot. Let's go ahead and get the y value that corresponds for x equals 3 over 4. So what we're going to do is we're going to take that x value and we're going to plug it back into the original function, not the derivative, but the original function. So I'm going to do f of 3/4 into the original function. So this is going to be 2 times 3/4 squared minus 3 times 3/4 plus 5. And I'll just throw that into my calculator. So 2 times 3/4 squared minus 3 times 3/4 plus 5, giving us a y value of 31 over 8, which doesn't mean a whole lot to me at least. That's going to be 3.875. That means a lot more, because then that will tell me where I'm at actually on the graph. So our ordered pair here is going to be 3/4, 3.875. And you can put them both in fractions or both in decimals, but 3/4 is 0.75. That's why I didn't really think too much about that one. All right, so we know at 3/4, 3.875. So 3/4 is right about there. 3.875, maybe roughly right there. Let's not be too precise. Something's happening. It's either decreasing and then increasing, or decreasing, decreasing, increasing, 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 decreasing. That's the moment, though, where we need to see what's happening around that point. So what we're going to do then is we're going to create some intervals. We're going to go from negative infinity to 3/4, because that's going to tell us what's happening to the left. And then we want to know what's happening to the right. So 3/4 to infinity. 3/4 to infinity there. So take a point in this interval, which make your life easy. If 0 is in the interval you're trying to figure out what's happening in, use 0. So f prime of 0, so that means I'm going to take 0, plug it into the derivative. 4 times 0 is 0. 0 minus 3 is negative 3. And we don't really care about the actual value. All we care about is if it's positive or negative, because then that'll tell if it's increasing or decreasing. Negative means that it's less than 0. Negative means that it's decreasing on that interval. So we know we're going to be doing something like this. It's going to be decreasing, traveling left to right into that point. Now let's take a test point in the second interval from 3/4 to infinity. So let's do f prime of 1. F prime of 1, so plugging in 1, because 1 is in the interval 3/4 to infinity. So 4 times 1 is 4. 4 minus 3 is positive 1. 1 is greater than 0. It's a positive value. That means it's going to be increasing on that interval. So we know it's going to be decreasing to increasing, indicating to us that this is going to be a relative minimum, because it's going to be decreasing and then increasing. If you want to be pretty precise, you could take a couple x values, plug it into the function. That will tell you if it's like doing something like this, like coming in a little bit slower, or if it's coming in pretty steep. Like, what is it actually doing? I'm just going to take f of -4 just to give me an idea of where I'm at on -4. Let's do -2 actually. Why go that far? Let's just do -2. -2 will give me a good idea if I'm coming in pretty steep or coming in pretty slow there. So I'm going to do f of -2 into the original function. So 2 times -2 squared minus 3 times -2 plus 5, which is 19. So -2, 19. So it's going to be pretty steep. So I'm just going to come in like this. And then we want to know what's happening on the other side of that. So let me do f of, let's do 4. So let's do f of 4. So it's plugging in 4 into the original function because I want to know what the y value that would correspond to that is, just to give myself a good idea of what the graph might look like. And that is going to be positive 25, so a little bit steep too. And there it is. There's our graph. And sometimes people are completely fine with like, all right, it's decreasing, so just draw a decreasing graph. Like, but if you want to be a little bit more precise so you get an idea of how steep it is or not, then you might want to take a couple x values. And obviously you could take as many x values as you want to get a really precise graph. But sometimes it's completely fine to just sketch in a decreasing graph and sketch in an increasing graph just to get, and to be honest, I do this in class all the time where we just draw a decreasing graph. Just to save some time in class. We just don't have the kind of time to go through and take x values and plug them in to get an extremely precise graph here. But since we decided that this is a bottoming out point, this is going to be a relative minimum. So it's going to, this point is going to be a relative minimum. And we don't have a relative maximum because we took the derivative and we only had a single critical value. So that's going to be the only critical value there. So relative min, and there's the graph.